This is a very good oscillator on 10 megahertz. I am measuring the sideband noise at various separations, and it's good enough to make it difficult to do these measurements. Have a look at these videos if you want to see in details what I have done to hardware in order to make measurements at wide separations. These are the data points I have taken so far. The scale vertically starts at minus 200 dBc per hertz, and 190 is here. And you can see the last point, the closest I have reached is 5 kilohertz, and there the level is minus 180 dBc per hertz. And it looks like a straight line, and I have extrapolated it, and it will be interesting for me to see at what point it starts to bend off. In this video I will show limitations due to software. First, I'm running at 96 kilohertz from the UADZ4, as you can see the setup here. This is the spectrum. It doesn't look so nice, but it's a little bit misleading because the peak here is calibrated to show 0, roughly, on the S-meter graph. The second biggest peak here is the mirror image, and it's suppressed by 20 to 30 dB. So energy-wise it's insignificant. Then there are non-linearity problems of the mixers, because the mixers are at the point of about 0.1 dB compression. I'm listening on the 2-channel direct conversion receiver here. Linear has a feature, the F11 button, and I have pressed that, and now what we see is not a signal from the sound card. This is an internally generated perfect sine wave. And I clear the correlation, and here you can see the spectrum, and it's collecting a correlation spectra, and you can see there is no correlation advantage at all, but there is some noise, and the noise floor I see is, I'm looking somewhere here for example, and you can see it is about minus 180 dBc per hertz, and there are nearby spurs also. And if I look at 5 kilohertz separation, that's here, the noise floor is similar. I can press F7 to add random noise, and the level where the noise is in bits, 9, 10, and you look here, you can see the noise floor is increasing. Here I have added something like 25 dB of noise. And now, of course, if I clear the correlation spectrum, like that, and then I wait, I expect the maximum correlation advantage to be these, how much was it? From minus 182 to minus 158. That's 22 dB. So no more than 22 dB is expected here. After quite some time, I now have a result at 5 kHz offset, correlation advantage 23.4, and the average power is minus 159.3. And then I go for the carrier. So I click on the carrier to get it centered in the filter here, like that. And then the carrier power level is 1.1 dB plus. These numbers give me minus 183.8 dBc per hertz. That's here. A little bit better than I have seen before, and I don't yet know why. Now it has been running for a long time. The result is a little unexpected. There is a sweet point here. This is obviously sideband noise. The reason for the slow slope upwards is unknown to me. Maybe it could be phase noise on the sampling clock of the sound card. And this structure here, it's a strong signal. It's only 10 decibels below the noise of the sound card. Anyway, I can save this image and read the noise levels from the green trace, knowing that at 5 kilohertz the value is this. And I will also now expand the spectrum and look at closer spacings. When I click here to expand the spectrum, I will lose information now, because data that comes outside screen will not be properly updated. But I can expand it this way also. And now I can see much easier what the green trace is. And I will evaluate the noise at closer spacings. I cannot go closer than this gap at 1.75 kilohertz, because at closer separations there are these aliasing spurs, and they are much stronger, even closer, and you can see it here in the spectrum. I will enable the internal signal generator by pressing F11. And then I will clear the correlation spectra, Alt Z, to find where the noise level is now on a perfect signal. This will take some time. No, now it's finished. And here is the noise floor. And I will have to add noise. I press F7. So I added a little bit of noise here. and then again clear correlation, and now I will wait. It's obvious there are fairly strong spurs here and here, for example, but in the correlation spectrum, the frequencies where I measured, these spurs are not so strong. The levels I see below 185 or 190 at the wider separations, they are a little bit, maybe significantly lower than the values I have with the receivers. But this isn't really satisfactory. I should have used the dual precision arithmetics to do the Fourier transforms to bring these problems down. But there is another alternative. For close range, I can use a lower sampling rate, and that will ease the rounding errors from the transform. And as you have seen already, at wider separations than about 5 kilohertz, there is some other problem. I don't know if it will survive or not at lower sampling rates, but I will try that now. I have added now a new version for the first FFT, using double precision floats for the FFT and for the window function in front of the FFT. The window is very important to have in double precision because rounding errors on the window would otherwise be correlated between the channels. And it's obvious the problems I have seen, didn't talk about it, but there was an asymmetry between the sides. It's no longer there, and there is no longer a sweet point at about 5 kilohertz. The noise is flat above that. This artifact is still present, and we can see one more here. More about that, hopefully, later. Anyway, now I can find that at 1.73 kilohertz from the carrier, I have a noise floor of minus 159.5 and correlation 18.2. I have clicked on the carrier to get the carrier level, and it's on the average, well, it's close enough to 0. I take the average of these two. And as compared to the previous value I obtained at 1750, which didn't change much if I stepped it around that frequency, is now about 3 dB better because of the double precision computations. And also I see a spur when moving the selected frequency a little bit up and down. Not very strong, just 1 or 2 dB. The flat noise floor here at 10 kilohertz above the carrier is minus 161 with 23 dB correlation advantage. Changing from single to double precision goes from black to red numbers in this table, and the difference is 3 dB at close range and very small at wide range. And the dual precision gives me points here, and I will look with larger resolution because this is close range. I will just continue a little bit further to study what I'm really doing. First, I expand the spectrum, clicking here. in order to see better the structure of the correlation spectrum, the green dots, to see if I can locate spurs in it. And indeed, yes. So all these spurs, I don't know the origin, they do affect the result I get. To try to get an understanding, I press F11 to enable the internal signal generator. It comes here, clear. And now it looks very different from before. If I click near, the noise floor is outside the screen here. It says nearly 100 dB improvement from -156 to -242. So this made a difference. I will try to look at the noise floor. Just step up here. And this doesn't look right. I will look into it a little bit better. Seems to be an error in the window function. Probably it doesn't start close enough to 0, so there is a discontinuity when the window starts. I think the criterion was -180 decibels when I set up the window originally. Here is the dual direct conversion receiver. The signal is at the maximum level, about 0.1 dB compression in the Schottky mixers. I have corrected the internal generator and I start that now and clear the correlation. And here is the noise floor down here. And to see it, I have to step up the scale. It's at -70 now. And if I enable again the direct conversion receiver, F11 again, it is very much higher here. So the rounding errors of the FFT or the window multiplication is no longer a problem. I have disconnected the Schottky mixers and replaced them with dummy loads. I have set the frequency now to 4 kHz from 10 MHz, where there is a peak in the correlated noise. The summed power is -158.6 with a correlation of 21.6. That gives me about -180 dBc per Hertz as a limit for how low noise I can see. And at 6.7 kHz, here the correlation advantage is 30 dB, and here 158.8. So 159 plus 30 is 189. I have reconnected the mixers and clicked on the carrier, the main signal, to read the power, which is plus 2.5 dB on the average. I forgot to do this calibration before I did the noise measurement, but I can equally well do it afterwards. There is a 2.5 dB error. Here is the limitation given by the sound card. I can see down to minus, well, maybe 182 or so at 1 kilohertz. At 4 kilohertz, I cannot see better than about 173 or so. Of course, if I subtract this, I can go down to minus 180 maybe, but the accuracy would suffer. When I plot it in the logarithmic scale, I can see that it's not useful at this range, where it was useful to use the notch filter to remove the strong signal and increase the audio gain. But at 1 kilohertz and below that, I should get reasonable results from this setup. So I will have a look to see what comes out. Here I have recorded 233,000 averages, and I am looking at the center peak, the carrier, at 10 megahertz, 10.0, and it tells me 10.0 because calibration is nearly correct. The level of the carrier is a little bit different between the channels, but on the average it is set to 0. I have now expanded the vertical scale and selected a frequency here where the white track is flat, means the average power spectrum, and I can evaluate that point here, and it is minus 159.5 dBc per hertz. That is with respect to that carrier that I just found to be very close to 0. I can now press G and then save this screen as some file name I invent. And then I can look at it with a pixel editor. But before doing so, I have expanded the X scale to get much better resolution. You can see the peak shape and that the average is very flat when there are fairly strong noise signals, but when statistics become worse, we have problems. But I can guess where the proper noise of the oscillator, which is not yet an oscillator, it works as an amplifier still. So I save this also, G mar 04B. So I can look at this also with the pixel editor. Before closing this screen, I evaluated the conventional way. This is at 40 Hertz, and the average power here is minus 141.85 with 9.6 on the average for the correlation advantage. So my conventional evaluation gives me minus 151.5 at 40 Hertz. That's here. So I can guess that the curve is starting to bend upwards. I also want to know how close can I go before entering the response of the main signal. So I press F11 to enable the internal generator and Alt Z to clean. And now this is outside. So I have to, here is that signal. I have expanded X and Y and centered the internal generator on the screen. And of course the peak here is very close to 0. It's plus 1 dB. And I want to know how wide. So I click here and read 0.5785. And on the other side 0.6004. The difference is 22 Hertz, which means at 11 Hertz from the center I have no influence of the main signal. But I can go a little bit closer because I don't need to go all the way down to minus 50. That is 200 dB or something. This is about 190 dB below the peak, and that is good enough. And I read 0.5797, and on the other side here 5993. So that's 19.6 Hertz. I can read starting at 10 Hertz offset, no closer than that. This is GIMP, the GNU image manipulation program. And I put the cursor at 10 megahertz, and that's on this peak, and I read 659 for the X coordinate. And if I move and place properly for the green line, that is where the curve saturates, I also see 659 because the spectrum is properly calibrated. Here I have 2 kilohertz offset, and the X coordinate is 1649. I was reading out the white track at this point, which is 431 in pixels and minus 159.48 in dBc per hertz. And I can read minus 20 dB gives me the vertical coordinate 657, and plus 20 dB gives 373. Here I can read the green curve at 679, that is plus 40 Hertz, and I read 376. The other side is 639, and there I see 403. So I use these numbers to compute decibels per pixels and hertz per pixel, and then I measure at plus and minus 40 Hertz and arrive at minus 151.8 and 155.5 dBc per Hertz. Minus on plus and minus side. 1.8 is very close to the 151.5 I got with the conventional evaluation. So this works fine, and I will use it to get many more data points. This is 400 Hertz, and it seems that the value starts to be uncertain. I can follow the curve here, but now it scatters too much above this frequency. So, well, I can try 500 Hz also as the highest I can reach with this configuration. This is 500 Hz and probably within 1 decibel. It's easier to read from the expanded scale, so I start here at minus 60 Hz. That's 80 pixels. That is 424 vertically. And you can see I guess where I should not take the 50 Hz peak into account. It comes here. And as it turns out, previously I guessed 424 on the compressed curve. So this was fine. And I will check the other points also. That image evaluation ends up in a table like this. These are the data points I get. At 10 Hz, here it's about minus 138. The squares, yellow, they are below 10 megahertz, and the green circles are above 10 megahertz. And I don't know why the curve is asymmetric. Maybe I am a little bit offset in frequency. I don't think it is important because the average between them should be the true value. I would like to go a little bit closer to the carrier. To do that, I need a smaller bin bandwidth of the first FFT, and that can be done by making the FFT larger. Now, that's not trivial because pointers in Linrad are only 16-bit. Once upon a time that was important for the Pentium 3 to make the pointers for the unscrambling of the transform small enough to fit in the cache memory, together with the array with the data in it. And that was long ago, and I have forgotten all the details, and there are several different versions of the FFTs. So there is another solution, that is to run the sound card at a lower sampling speed. Now, I cannot do that because the lowest speed for the UADC4 is 44,100 Hz. But I can use another sound card. This is the Delta 44 running at 8 kHz. That would allow me 5 times closer. That is 2 Hz from the carrier, and that will be sufficient. I have collected 600,000 averages, and as you can see, the correlation is the same as the theoretical. So I don't see that funny phenomenon that I have in the UADC4 with the correlation between the channels. Not very surprising because the Delta 44 has 2 ADC chips with 2 channels in each, and therefore the 2 channels INQ for one chip and INQ for the other channel in another chip. So there is no correlation between the channels, or at least it is very small. And very close to the carrier, sensitivity is not as much an issue as at larger separations, because I don't expect the dBc per hertz to be extremely high here. Now it has been running for about 10 hours. It's obvious that frequency stability is a problem. The white and the yellow shows the spectrum for the latest 558 spectra, while the yellow is correlation and the white is the power spectrum. The green is the accumulated correlation spectrum over the 10 hours. And you can see at close range, yellow and green are the same. But at wide range, the green goes down below the yellow. So I can use this information, but it will be different on upper and lower sides of the frequency, particularly at close range. Now some more hours have elapsed, and the frequency has drifted again by 1 hertz or something. The frequency drift is in my 2 oscillators that are locked to each other and that run 700 hertz below 10 megahertz. There is no temperature stabilization on them, while the signal comes from the vent cell, which is temperature stabilized. But this will not affect the measurement much. The signal I'm measuring within a bandwidth that includes everything. And here is the correlation advantage, which is 0.0. And the carrier level comes out as 0.1 dB. So that's the thermal drift on amplitude of the system, and I will neglect this. I can read the coordinates of the correlation spectrum, the green dots, like this. This particular point is 938 by 214. And then I can evaluate the true center of gravity of this peak to take frequency drift into account properly. Then I use Excel to compute the center of gravity for the linear power that goes from minus 30 dB something, minus 35, up to minus 38 at the high side. And the center of gravity is x coordinate 955.2. I use this saved image to evaluate the noise. I know that minus 133.7 is the white curve when it crosses the green line here. That is pixel 460 vertically. I get the scales by reading the pixels for the dB scale as well as for the frequency scale, which I have on top here. And then I make a table of dots from the green curve and I try to average in a suitable way. So if I want to read here, I would place it, I can imagine where the line has to go here. And then I make a table of these numbers, put them into Excel and compute the frequency. That's just to check that I didn't make any mistake. And then the noise and the logarithm of the frequency. And when I plot it, this is what it looks like. It's the red points, and they fit perfectly well to what I observed at larger separations. So this works, and I'm still using the selective amplifier as an amplifier, feeding it with a vent cell ultra-low noise oscillator. Here is a measurement made with a FSWP from Rodin Schwarz on this particular oscillator that I'm using. And I have taken points from this curve and marked them in my diagram. They come here, 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 and here. So I will make a new measurement of this Wenzel oscillator with my system to see where the data points come. I have detected an error in this graph. The correction of 2.5 dB, I made it in the wrong direction. So this is what it should look like. And then I see that I can measure down to a little bit below minus 180 at the worst frequency, 5 kilohertz. Now I have shifted this curve showing the limitation given by the sound card downwards by 5 dB, and I have also put back these points now in red, the first points that I made with the dual precision FFT, and that I rejected because they didn't seem to fit the straight line I had at that time, and they were below this curve where it was placed before. But it seems those values were perfectly okay, and this limitation by the sound card, it seems it is not as bad as I have been thinking. Here is the setup I have been using in this video so far. Signal source, amplifier, attenuator, and my selective amplifier, and an attenuator to set the signal level to fit the receiver. I have now changed to do it like this instead. The oscillator, the same amplifier, 2 dB more attenuation, and then the receiver to analyze the performance of the ultra-low noise oscillator in a as similar as possible way as I did previously in this video. Here is the UADC4 at 44,100 Hz. I have clicked on the carrier and check where the level is, and it's still correct, it's at 0. It's obvious that this oscillator is now noisier when it's no longer filtered through my selective amplifier. I can see that the correlation spectrum here, the green trace, is pretty flat. And if I click on it at, let's say, 2 kilohertz here, the correlation advantage is 12 dB, while the theoretical limit is 25. To see better, I will expand the vertical scale. I see 159, minus 159 dBc per hertz, and 12.8 dB advantage. That's minus 171.7, and it comes here. I have saved the screen, and also this one, which is expanded in the X direction. Now, this is Linux, and I have another desktop. I click there, there. And here I have the same time recorded with the Delta 44 at 8 kilohertz. And I should get the same results when evaluating this. But this goes to closer frequency spacings. First I check the carrier level by clicking on the carrier, and as you see, the carrier comes as 0 on the S-meter graph. At 20 Hz offset, the level is like that, minus 129.9 with a 15.5 dB advantage. That's minus 146.4 And the point comes exactly on the line I have from the selective amplifier. Interesting. I have evaluated the Delta 44 screen with the pixel editor, and these are the numbers. I will feed them into Excel and look what it comes out as dBc per hertz. I evaluate like this, take the average of the upper and lower noise level and plot it, and it's the plus signs here, 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 and here. Very close to the performance I see through the selective amplifier. These are the data points from the UADC4. And here is what I see with the pixel editor from the UADC4 screen. They evaluate like this, and I made some small mistake when setting the frequency. Plus minus 128 became 133 and 125. That's close enough to be valid to use the average of these two numbers here. Those data points are the plus here, 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 and here, and here. So at above 200 Hertz or so, the selectivity of the crystal filter gives a significant improvement to the noise of the Wenzel. But closer in, it seems that the selective amplifier now no longer adds any noise. And it will be interesting to give it feedback and see how it behaves as an oscillator. And that will be the next video.